Hello and welcome to the lesson on the chi-square test for independence. In this test we have count data now for two variables, and we want to test if the variables are independent. So I will use the same example that's in your notes. So actually this time I'll just input the data manually. So I've done that over here, and I'll just copy and paste. So our observed values, I've just put them in a vector here and called that data. But with the chi-square test of independence, it's nice to have our data in a matrix format. So we can convert this vector to a matrix by just using this command here, matrix, and inputting our vector called data. And we want it to have 3 rows, and that's going to form our observed values. And then with these two commands at the end, I'm simply adding some names for the rows, which are the 3 different locations, and the columns, which are the 3 different beverages. So if you hit enter, and now hit observed. Okay, so this array here forms our observed values. So we have 3 coffee shops, A, B, and C, and 3 different beverages sold there. Light roast, dark roast, and French vanilla. Now we want to see if there's an association between location and beverage order. So for this data set, you have the number of orders of each beverage type at each location, right? That's the values in this array here. And now our null hypothesis states that the proportion of orders of light, dark, and French vanilla are the same at each coffee shop. So we'll test this using the chi-square. Now the easy way is to use the built-in function that we saw last time, and we just input our observed values. And we get a chi-square statistic of 18.561, and the p-value less than, say, if our alpha level was 0.05, then our test would be significant, and we conclude that location and beverage are not independent. Now, that's easy if all you want is the summary of whether the result is statistically significant or not, but we might actually want to see our expected values or calculate some residuals and maybe plot those or something. So let's go ahead and do the chi-square more sort of the longhand method. So the first thing we'll do is determine our expected values. So I'll copy over the command here. Now what I'm doing is, in this first line, I create a matrix 3 by 3, and I just make each entry 0. So I'm just setting up a base matrix that I can update the value to give my expected values. Now, to actually calculate the expected values, I'm using a nested loop here, right? So I have for I in 1 to 3, and then for j in 1 to 3. So what I'm doing is I'm indexing each row and each column. And what I do is to define the expected value in row I and column j, right, where those range from 1 to 3 in each case. This value here is just the formula for the expected frequency that's in your notes converted into our syntax, right? So I take the sum of the observed values in row I times the sum of the observed values in column j, and then I divide that by the total sum of the observed values, and that gives me the expected frequency in row I and column j. So for instance, if I wanted the expected frequency. So if I wanted the expected frequency at shop A for light beverages, or the light roast beverage, that would be I and j equal to 1. Okay, so hit enter, and you get your array of expected frequencies. We can give that array some row and column names as well. Let's do that just to make it a little bit easier. So I'll just use this command and change it to expected. And then same thing for the column names. Let's look at that matrix. Okay, so these are our expected frequencies. So note that under the null hypothesis, the proportion of orders of light, dark, and French vanilla are the same at each coffee shop. Right? So we can see this now from our from our expected values. So if we take, say, if we go to location A, we take the ratio of light to dark, that's 14 to 57. So if you take 14 divided by 57, that's 0.245614. Okay, now go to shop B and take the ratio of light to dark. That's 28 to 114. You get the same value. And of course, same thing at shop C, right? Similarly, if you were to take the ratio, 57 to 29, that's the same as 114 to 58. You can see that, 57 to 29 and 114 to 58. And similarly, the ratio of light to French vanilla would be the same at each shop. So 14 to 29 should be the same as 28 to 58. Okay, so that's sort of just explaining what we're saying by the null hypothesis. Now let's actually calculate our chi-square statistic. So I'm going to use another one of these nested loops. So originally I just set the chi-square value to 0, and then I'm going to update that with my loop. So again, I range for each row and column, and then my chi-square value becomes the previous chi-square value updated with the observed minus the expected frequency in row I, column J squared, divided by the expected frequency in row I and column J. So that's just your formula for the chi-square statistic, right? The difference observed minus expected squared over expected. So hit enter and print the chi-square statistic of 18.56088, which is the same value that we obtained before. We could also calculate our critical value. And I think we saw this command in the last lesson. Now we have 4 degrees of freedom, and you get 9.4877. So the obtained value is larger than the critical one. So again, we'd see that we were rejecting the null hypothesis. We can calculate the p-value. And remember, we have to input that option lower dot tail equals false, and you get the same value that you obtained before. Now, to actually see where our differences lie, we can use the residuals. So if you remember in the first lesson on the chi-square, the residuals weren't all that helpful. It was pretty easy to see how the data deviated from the expected frequencies. In the two variable case, much more difficult, so it'll be helpful to calculate the residuals. So again, we're going to use another one of these nested loops. Essentially follows the same idea as for the expected matrix, but remember the formula for the residuals is really all that's changing. So you just take the observed minus the expected divided by the square root of the expected. So hit enter. You can take a look at that matrix. And so these are our residuals for this problem. So what can we see here? We see that at shop A, there's a higher proportion favoring the light roast as opposed to French vanilla, right? Light roast has a large positive residual, and the opposite pattern is true for the French vanilla, right? Now we've got a negative residual here. Now the opposite pattern is true for shops B and C. There seems to be a relatively stronger preference for French vanilla because the residual is larger than the residual for the light roast, right? 0 is larger than this negative residual here. And you have 1.313 positive residual versus this negative 1.512. So that really helps to clarify how our data fail to follow the distribution of the null hypothesis. Now we can make a few visualizations of our data. One way that helps visualize sort of the residuals is something called an association plot. And the command is simple. All we have to type is this. Hit enter, and you get your association plot. So let me just shrink this down a little bit. We can take a look at it side by side with the residuals. So remember, for shop A, we were saying there was a large residual for the light roast and a larger negative residual for the French vanilla. That's exactly what we see here, right? Light roast has the large positive residual, and the opposite pattern is true for the French vanilla. And then we see the contrasting pattern for shops B and C. Here, the residual is larger for the French vanilla relative to the light roast. So at shop A, there's more of a preference for the light roast beverage, and shops B and C, you have a stronger preference for the French vanilla. We can also create a stacked grouped bar chart. So we would need to modify our data a little bit. You could do this in R. For a smaller data set like this, it might just be easier to do it in Excel or do it manually. I've already manipulated the data set, so I'll load that up here. It's called beverage data. And you can see I've just changed the format around. I've got 18 entries, so one for each observed value and one for each expected value. So these are my counts. Right here are the observed, and then I have the expected values here, and then I simply state whether the type of beverage, and then also the shop. So when you have this, when your data in this format, it's easy to make a stacked and grouped bar plot to compare your observed and expected frequencies. So I'll copy over the command, and we're going to use ggplot, so make sure you have that package loaded. And so at the beginning here, we're just setting up our data is coming from this beverage data frame, and then we're going to have the observed and expected values on the x-axis, and the counts will be the heights of the bars. And we're going to fill them with the location. And then for the heights of the bars, right, we're just going to use the identity. We don't want to calculate means or anything. We just want to plot the heights that are actually listed in this column. And then we're going to group things by beverage. So you'll see how that looks like in the plot. And then we just add some titles to the plot. So hit enter. And let's take a look.